merge sort. We're going to be merging two ordered linked lists. I ran into this problem on LeetCode, and it took me a while to get to a solution. And when I did get to a solution, it was highly inefficient, and it just took too long, and I got a runtime error. So I did a little studying, and I looked more into it, and I found a pretty good solution that worked, and I was able to take the concept and actually code it out. So just to help myself understand it better, I'm gonna try to explain it to you guys on LinkedIn. If I do a good job, let me know. If I do a terrible job or I miss something, please let me know, and then we can interact in the comments. And I'll also link to some of the resources that I use to help me grab this concept. So starting off, we're gonna merge a linked list. So we're just gonna fill this in with some numbers. So working with a linked list, you have pointers that are pointing to the next place in memory when you're dealing with it. So our goal here is just to make sure that that by the end of it, we have one single linked list. By creating a node, which was going to be the start of my new linked list or the head of my new linked list that I was going to return. So we can call this node, we can call it, let's see, results, right? Results node. And in there, we can start it off with a node that's equal to node, because we want our head, to point to something. You can have it start at negative infinity if you want to, but we have to have it started. We have to have an actual value in this. We have to have an actual node in here. So we're going to start it off with, like, let's say we have cur, which right now cur.value is equal to no. So I'm going to use a different one for that. So cur.value is set to no. So cur right now is pointing to the head of this linked list. So this is linked list 2, and this is linked list 1. And this is our results linked list that we're going to return. And this right now, cur is a pointer that's pointing to this linked list. All right? So now the next thing that we need to do is we need to start merging this linked list. So we can start off by comparing the values in the linked list. If we just approach it one at a time and just compare the values. So as long as these linked lists are, both of these linked lists are not no, we'll keep on traversing through this linked list. Now we're going to deal with merging these two linked lists together. So when we're merging this linked list, we're merging them in order. So we have to compare which value is less than and which value is greater than, right? So we can usually handle that with two conditions. So our first condition, we check, okay, which one is L1 less than L2? Okay, L1 is less than L2. So we want to take our current node, or cur as we're calling it here. We want to point it to L2. So cur.next now is pointing to L1, not L2, L1, because that's the ledger node. And now we want to move L1 to 1 because that's already been, because we've already pointed to it. So now we just need to update L1 value to point to the next node in its own list. And then once now cur.next is pointing to here, we need to update cur as well. Since we've updated L1, we need to move cur to equal cur.next, which will be over here now. So this is where cur is pointing.
So this step is pretty much like the last one. So what we're going to do here is we're going to check our first if condition. Is L1 less than L2? Yes, it is. 1 is less than 2. So what we're going to do here is we're going to take our current pointer and equal its next value to be equal to L1. And then after we've done that, we're going to take L1 and equal it to L1's next value. So we'll move that up, and now we're going to take our actual current and equal it to its own current.next, which should be the last place L1 was at. So current is just pointing to the smallest to the last smallest number. It's just keeping track of the tail of the last smallest number.
Cur is always pointing to the tail of the smallest value. Now we're here. So here we're comparing values of L3 and L2. Which one is smaller? In this condition, L1 isn't the smaller one. So now our first condition doesn't work. Our second condition, which is else. Okay, so else, if it's greater than, else, which means it's either greater than or equal to. That doesn't matter. If it's greater than or equal to, we're going to do the same thing. We're going to take cur wherever it's pointing, we're going to take cur and then point it to the lesser value or the equal value, which our else statement covers. So here, cur is going to be pointing, cur points to L2, and then after that, we update L2 to equal L2 dot next and move it up. And then we take cur to equal cur dot next, because cur is always at the smallest, is always at the smallest node value. It's always at the tail of the smallest node value. Now that we're here and we've updated the values, we go back into our loop and then we compare the values again. So here we're comparing 3 to 3. Which one is smaller? We see that L1 is the smaller value, so that activates our second. So pretty much what's happening here is a pattern. Cur is always consuming the lesser value, and then after it's consuming the lesser value, that node that was currently there, or that linked list that was currently there, moves on to the next node in its list, and then cur moves on to the next, moves on to the place where it just consumed it. Cur becomes that next node, and then we run our operation again, where we're only checking for a condition where L1 is less than L2. If that happens, then we consume what's up here in L1, else we consume L2. So this handles our situation where it's equal to or less than, equal to or greater than. And we can do vice versa too, where we just check which one is greater than. It doesn't really matter, it gives us the same results. It's up to you to decide which one you want to be your default in the situation where it's equal to. So going back to our situation. All right, now we're getting close to the end of our list, and this is where we're going to add another condition outside of our current loop. So first we evaluate the situation where we're at our current, and then we compare which one are we going to consume. Is L1 less than L2? L1 is less than L2, so we're going to consume that. Our current .next pointer is going to go ahead and point to this. That's our next thing we're consuming. We've established a connection here. And now L1 moves over here and it's equal to no. So there's nothing going on there. And then we take cur and update it to be equal to L1. We mean to update it equal to cur.next. So now that's the current state. That's the current node we're at. L1 is equal to no. And now our condition, or our while loop or for loop, whichever one was running, which one you chose to use it, at this time says, okay, we're checking to see if both of them were true, if both L1 and L2 are true. L1 is no, so by default, that evaluates out to a false value. So that ends our loop, and our loop is over with. But we're at a point where we don't need the loop anymore. This is where we finish off the rest of these nodes, because we can assume that the last value that we consumed while our loop was valid was the smallest value possible at that time. And then after that, all we need is a condition outside of this loop that checks for one thing. It's going to do cur. It's going to check if cur. It's going to assign what cur.next is going to point to. So cur.next is going to be equal to L1 or L2, and it's only going to be equal to the one that evaluates to true. So L1 is no, so L1 evaluates to false. But L2 still has a value in there, so that's going to evaluate to true. So our cur.next now is going to point to L2, and then if we and then we don't have to move it at that point, because at that point we've already removed this. We've already removed this linked list, and we no longer need to check that because we've equaled cur.next is equal to the remainder of L2. So we can put L2 or L1. It evaluates that L1 is false, so it's not going to equal that. L2 is true. So now our cur.next is equal to the rest of this array, completing our merge sort. And now when we return it, you gotta remember that at the beginning, we created a results node which had a no value to start off with. So at the beginning, results node, the head for results node was pointed to no. So when we return our value for our answer, we need to return results node dot next. Because if we return results node, we're going to include the no value that we started off with. Just for a reminder, this no value is what we started off with, and then cur was originally no when we started off here, and then we did cur.next to give it a value, but that results node, no value was still part of our results node linked list. And then when we return results node.next, we're just only returning everything this way that goes through this path. It doesn't return that no value. So in the end, our linked list is still valid, and we've used them, and we haven't used them. We've only used O of one space because our no value doesn't take up any space. I might be wrong on that. I don't know the inner workings of no in JavaScript, but no is pretty much an absence as well, assigning absence in a variable. And then the only thing we've done here is just move the pointers to point to different directions and assign them to a new linked list. L1 is equal to no, L2 is still valid, and we haven't created any additional space. Linear, so that's for the space complexity for that would be O of 1. And then when we're looking at the time complexity, we're looking at a time complexity of O, M plus N. If you want to do it the other way, O, N plus M, where we're comparing the values of, okay, depending on the worst case, if this list is extremely long or this list is extremely long, or whether they're both the same height, this covers that situation, because depending on the length of the list, it could give us, it would determine how many operations we're going to do. If both lists are extremely long, that's how long it's going to take it. But if both lists are the same, it's still we're still adding both operations to it, because we have to visit every single node, except when we get to here, then we just assign the rest. Well, then we just assign the rest off. We just assign the rest. So that is the time. This is the time complexity. That's the space complexity. And if you want to try solving this and actually coding it out, I'll post the link to the LeetCode. I'll post a link to the LeetCode question, and you can solve it in whatever language you have. For me, for my purposes, I solved this in JavaScript. A good challenge if you want to try this problem and you've already solved it, try to do it recursively versus the iterative approach which I took. You can try the recursive method and let me know how that goes. Thank you.